Okay, thank you very much for the introduction and invitation. So today I would like to be talking about axion domain wave formations and the cosmological and phenomenological implications. In particular, I want to show that the axion domain wave can be formed in string axiverse. Therefore, by searching for the cosmological and phenomenological implications, we can indirectly prove the string axiverse. So this talk is mainly based on those couples of papers, and basically they are in collaboration with Sumi Takahashi, who gave a talk yesterday, and Naoya Kitajima, who is an assistant professor in Tohoku University, and Kai Murai, who will give a talk tomorrow, and Junsop Lee, who is a master course student. Okay, so this is the plan of today's talk. Basically, we have four parts. Introduction. So let's first define what is axion. So I think the axion definition is like this. So first, the axion should have a periodic field space satisfying this condition. Here, f phi is the decay constant, which represents the size of the field space, I mean the physical field space. In addition, we also have an approximate shift symmetry. From the periodic condition, we know that the potential should be periodic. From this approximate shift symmetry, we know this potential scale should be much smaller than the decay constant. And also we know that axion naturally have some small mass. So this kind of axion have many cubic completions. We can have this kind of axion from the spontaneous symmetry breaking of some Petrogreen symmetry or some global symmetry, because axion can be the non-Boson boson can basically satisfy this condition. Also, we can consider some string theory or M theory. By compactifying some extra dimension, we can have the degree of freedom behaving with this kind of property. Given the previous definition, I want to say that in any axion theories, we must have stable domain wave configuration. Because we have approximate shift symmetry and we have periodicity, so the potential must be bounded above and below. And once we have one of the minimum of the potential, then immediately we can find another minimum due to the periodicity. Of course, those minimum can be physically equivalent, but connecting the minimum will provide the domain wave configuration. Sometimes the domain wave configuration and the degenerate vacua can be more. And in this case, we can the number of the degenerate vacua in the physically equivalent physical field space is called the domain wave number. For instance, if we consider this kind of potential, which characterizes the case with domain wave number 2, we can see that we have a physical inequivalent vacua. Connecting the adjacent vacua, we can also form a domain wave. This kind of domain wave configuration can be formed in the early universe depending on the cosmological history. The well-known scenario may be the phase transition of the approximate U1 global symmetry. In this case, we can have some string domain wave network. I will not discuss in detail today, but I want to say this kind of scenario can apply to the U1 SSB scenario. On the other hand, today I want to focus on the possibility for generating the domain wave from inflationary fluctuation. And this kind of possibility works within the axion EFT. And therefore, it can apply to not only to the U1 SSB case, but also apply to the string axiverse. I will show that this kind of axion will, axion domain wave will have it is without a string, cosmic string. So we can have a pure domain wave. So let's discuss in detail. Let's consider the axion has a mass much smaller than the Hubble parameter during the inflation. Then we know this action undergoes some random jump. So at some field point after, at some position after inflation, we can only tell the field value of the axion in a probability way. The probability distribution is actually characterized by two kind of parameters. One of the parameters is the average field value in the observable universe. The other one is basically the Hubble parameter during the inflation. It represents the variance of the distribution. More precisely, this kind of Hubble parameter also describe the power spectrum of the excited mode for the axion field. It is basically a scale invariant power spectrum in the super horizon scale. This is similar to the inflation theory. Inflation has the fluctuation, which is almost scale invariant in the super horizon scale. Okay, so let's first consider the average field value is 0. Then this means that in the half of the volume of the observable universe, we have the axion field slightly towards the left vacuum. And in the another half of the volume of the whole universe, we'll have the observable universe will have the axion field around slightly around bias to the right vacuum. Then when the Hubble becomes comparable to the mass of the axion starts to oscillate about the nearest vacuum. The axion around x1 will oscillate around L vacuum. The axion at x2 will oscillate around right vacuum. Therefore, connecting the two positions, we will find the domain wall. So in fact, we can find many domain walls. Therefore, we can easily form the domain wall network, basically the scaling solution. In the order 1 Hubble volume, we have order 1 domain walls. This kind of formation do not provide cosmic string because this is kind of similar to the zip symmetry breaking. If we have spontaneous zip symmetry breaking, we don't have string. We only have the cosmic, the domain wall. However, it was considered that the stable domain wall from inflationary fluctuation is not stable unless serious fine-tuning. This is because the average field value is naturally not 0 because during inflation it also undergoes the random jump. So naturally it is not 0. Then we need to take into account the population bias. And numerical simulation says that the domain wall network is to decay fast if we have even small population bias. In the following, actually, I will show that this is not correct for the inflationary fluctuation. Actually, the domain wall network is stable against population bias. And therefore, we do not need significant tuning for having a stable domain wall network from inflationary fluctuation. And I will use this fact to discuss the axion domain wall from string axiverse. To show my claim, I want to employ lattice simulation for the domain wall evolution. To this end, I consider this symmetric phi-4 theory as the approximation. Actually, this is the same setup as the previous study. I think this is a good approximation because around the hilltop of the axion potential and the cosine potential, we can have this kind of expansion. And in this kind of formation, the relevant field range is around the hilltop. In the following, I will solve the equation motion from this potential by taking into account two kinds of initial condition. The first initial condition is the thermal fluctuation. This is characterized by the white noise at the super horizon scale. The other one, this is the initial condition with causality. So if we take the 2-point function separated by the super horizon scale, we will find there are no correlation. So therefore, this is a white noise. On the other hand, I want to emphasize that inflationary fluctuation should have scale invariant power spectrum for the fluctuation. This is similar to the inflation case and the inflaton case. Inflaton can solve the horizon problem. So basically, we have some beyond causality, property. So the important thing is we take into account this kind of scale invariant fluctuation. This is the numerical result by solving the classical equation motion for the domain wall network. And I show you some snapshot for the domain of configuration at the large enough conformal time. Here I take the population bias to be 0 for a while. We can see that in both cases, we have the scaling solution. Basically, we have the order 1 domain wall within the order 1 Hubble size in both cases. But the structures are quite different. In the white noise case, we can see the structure of the scale of the Hubble. On the other hand, in the scale invariant case, we can see the many many structures with different scales. For instance, if you look at here, we can find a large void, and here we can find some middle-sized void. So this is because of the initial condition of the respecting the inflationary fluctuation. We can also understand the formation of large void from the previous mentioned the random jump behavior. So even though we have the population bias in the large scale to be 0, if we focus on the smaller, region, and we take the average of the field around this region, we also have some behavior of random jump. So it is naturally to be non-zero. Therefore, we have locally we have some population bias. Therefore, most of the field around here can settle into say the left vacuum. Around here, we can have most of the field settle into the right vacuum. Therefore, we can have large void and large scale domain wall. This kind of domain wall rarely, they disappear because of the super horizon nature. From this kind of argument, we can also say that this kind of network can be stable under the population bias. So here I show you the population bias is 0 in this volume. We can enlarge the scale. We can enlarge the volume, and by fixing this kind of configuration. And then in the larger scale of the volume, we can also have some random jump. Therefore, naturally, we have the bias of order 1. And since this region is stable, therefore, totally, we also have the stable domain wall against the population bias. And this is a numerical result by taking into account non-vanishing population bias. Again, the left-hand side shows the case of white noise. Right-hand side shows the case of scale invariant case. So horizontal axis is the conformal time. The vertical axis is so this is similar to the area parameter, which is the domain wall length per unit Hubble scale. So I show you the results from 2D simulation because of we can have a better resolution, but we also check the 3D case as well, and the conclusion do not change. The difference between the two figures are the values of the population bias that we listed. In the left-hand side, we only listed the population bias smaller than the order 1%. Here, this yellow one is the 1% population bias. Here we have 0.1% population bias. We can see that even with the order 1% or smaller than order 1% population bias, the network decays. On the other hand, in the scale invariant case, I listed the older one bias. And even with older one bias, we can see that it rarely decays. Therefore, this confirms the previous argument. So with scale invariant initial condition, we can have the domain wave network long-lived if the population bias is smaller than order one. From this kind of given the stability against the population bias, we can discuss the scenarios of the domain walls from inflationary fluctuation. So we need to consider the scenario satisfying this condition. One possibility is to consider the decay constant is around the Hubble parameter. Then the distribution of the axion from the due to the inflationary fluctuation has a variance, around the field volume. Therefore, it is natural that this distribution covers the potential hilltop and satisfy this condition. We need to remind that the Hubble parameter is smaller than 10 to 13 GeV because of tensor to scalar ratio bound. Therefore, this kind of scenario means that decay constant to be also smaller than 10 to 13 GeV to have the domain wave formation. The second possibility is that this to take into account the fact that this decay constant is some dynamical, the expected value of some dynamical field. This is the case for various UV completion. Say this is decay constant is some expectation value of some Pechekin Higgs. Then during inflation, if this Higgs is light enough, then we can have different field value. So sometimes we can have the decay constant much smaller than the one at the present universe and the bed, or much larger than the today's one. Therefore, we may satisfy this kind of condition during inflation, but afterwards we can have different decay constant. The third possibility is that we may consider we have many axions. Then even if this Hubble parameter is smaller than the decay constant, we can compensate, and some of the axion can satisfy this condition. And the last condition I came up is the possibility that we have some mixing. So in this case, we have more than one axion, but one of the axion is settled around the potential minimum, which may be due to the small Hubble parameter during inflation, and another axion may be the inflaton. Then we can change the non-inflaton axion by a phase of pi. Then we can flip the potential to the hilltop. Then we can have the domain wave formation. In particular, the first three possibility do not depend much on the axion potential shape. We may even have this kind of shape. Thanks to the periodicity, we can still have the degenerate vacua, and therefore we can have the domain wave formation if we have certain distribution. I mean, if we satisfy this kind of condition. Usually this is difficult. This kind of scenario, possibility is not trivial because it is difficult to define the population bias. But since here we have insensitivity to the population bias, we are sure that even with this kind of generic axion potential, we can form the domain wave. Now we are ready to discuss the string axiverse. In string axiverse, usually we have many axions, and usually the decay constant is around 10 to 16 GeV. But according to Dodi's talk, if we have many axions, we may have smaller decay constant, and this is very good for this kind of scenario that I will be talking about. But anyway, so what I want to say is that in the string axiverse, this kind of condition can be easily satisfied because we have many axions. And if we have many axioms, this decay constant can be smaller, then again, it is easily satisfied. And once this relation is fully satisfied, it is unnatural that we don't have any domain wall. Therefore, it is very natural to have domain wall in the string axiverse. Okay. Then I think it is more important to discuss the cosmological implication of the domain wall, because that can be an indirect proof of the string axiverse. It is well known that if we have a stable domain wall, we have notorious domain wall problem. Therefore, we need to solve it. Therefore, only the valid cosmology should be without the domain wall problem. And with this kind of constraint, we can have some implication. For instance, the first possibility is to solve the domain wall problem is to consider the domain wall network decays in early universe. This may be due to some potential bias. And if the domain wall collapses, then we can produce some gravitational wave. And this gravitational wave can be proved. Another possibility is to consider some small tension. Therefore, this domain wall never dominate over the universe until today. And this kind of domain wall may naturally live until today around the present universe. And if the domain wall couples to some of the particles, we can have some implication. For instance, if we have this domain wall coupled to some photon, then we can have some cosmic birefringence. So let's first discuss this possibility. For concreteness, let's consider this kind of potential. So the first term is the cosine term with domain wall number 2. So it has physically inequivalent degenerate vacua. The second term has a cosine term with domain wall number 1. So it lifts one of the vacua. After the domain wall formation, scaling solution is formed. With this condition, when this condition is satisfied, namely the tension times the Hubble parameter is around the potential bias, we can have most of the domain wall collapse. Then we solve the domain wall problem, and we predict gravitational wave because of the collapse of the domain wall. So this is an interesting possibility. However, until now, until our work, there is no concrete study for predicting the gravitational wave from numerical lattice simulation. But there, of course, are nice works by studying the scaling domain walls with the vanishing the potential bias. And people, have some cutoff in time to check the spectrum, to predict the gravitational spectrum. And this time, it can be calculated from here. So this is kind of semi-analytic analysis for predicting the gravitational wave. The difficulty for the numerical simulation may be as follows. So if we want to include the potential bias, we need to guarantee the scaling solution. Therefore, we need to have the potential bias small enough. If we have potential bias small enough, we need to have a long enough calculation time, simulation time, so that we can have the most of the domain wall collapse to produce the gravitational wave. If we want to have a long calculation time, then we have to pay the price of the resolution, because this is expanding universe, and we consider some fixed co-moving box volume calculation. Therefore, we have several requirements that contradict with each other. With this kind of background, we perform the first lattice simulation of the gravitational wave from decaying domain wall. The key point or the trick of our analysis is to introduce time-dependent potential bias. So this potential bias is 0 at the beginning of the simulation. Therefore, we can form the scaling solution. After the scaling solution is formed, we turn on the potential bias, and this bias is large. Therefore, soon the domain will start to collapse, and soon they disappear. Therefore, we can, satisfy the previous requirement to get at the same time. But of course, this is not completely consistent with the constant bias case, but it is a very good approximation for the case really the potential bias is time dependent. And this is the case if the axion get the potential bias similar to the QCD axion-like potential, which depends on the cosmic temperature. Well, this is a numerical result
2 minutes.
from lattice simulation. Okay. So I show several lines. The different line correspond to different time slices. I show the gravitational wave spectrum, and time increases in this direction. In the first few line, we don't have the potential bias. Therefore, this is a spectrum for from the scaling solution. And we can see that indeed the peak follows the horizon scale. In addition, from our analysis, we found there is a new contribution from here, and this new contribution seems to be dominant. We consider this new contribution comes from the collision of the domain wall at the last moment of the decay of the network. And at this last moment, the wall will be accelerated due to the false vacuum, due to the potential bias. Therefore, they are energetic. Therefore, the produced gravitational wave is also enhanced. So we have dominant contribution. This is the case for the scale invariant. And we apply our analysis to explain the nanograph data. And this is a simple possibility. We can consider the domain wall coupled to the QCD, the sun model QCD, Gigi-Childa. Then this domain wall will acquire a time-dependent potential bias. Interestingly, when the QCD phase transition happens, we have this kind of potential bias appear. So it naturally explains the nanohertz, because most of the domain wall with small enough tension will disappear around the QCD phase transition. Unfortunately, this kind of scenario cannot be consistent with the string axion because the decay constant may be too small. Because we want to have the axion produced from the domain wall collapse decay before the Big Bang nucleosynthesis. We need to have the decay constant small enough. But in general, string axion can also have the domain wall, and whose collapse can give the gravitational wave, and which can be proved in the not too distant future. Okay, maybe I don't have enough time, but I will flash some slides for the second possibility. So we consider small tension, and we consider the axion coupled to the photons. Then we can induce some cosmic birefringence. In particular, this is the rotation of the photon polarization. So we may consider this photon is the CME photon. When this photon go across the domain wall, we can have the polarization rotation. There are two kinds of observable. One is the isotropic cosmic birefringence. We have 3 sigma hints. We also can constrain the anisotropic cosmic birefringence. And in fact, the scaling domain wall without a string can naturally explain isotropic cosmic birefringence. So this is a kind of prediction. It is 0.1, order 0.1 degree with order 1 C gamma, and this is consistent with the observation. If our scenario explains isotropic cosmic birefringence, we can predict anisotropic cosmic birefringence because the domain wall at the last Cartesian surface is kind of have certain distribution, and this kind of distribution introduced some anisotropic cosmic birefringence. And this kind of anisotropic cosmic birefringence is calculated by the lattice simulation, and we found that in the scale invariant case we can prove our scenario I mean very soon. This is the end of my talk. I have talked about that Axion model always involves stable domain wall configuration, and domain wall formation may be natural in string axiverse. In particular, if we have many axions. Avoiding the domain wall problem, we can have some implication, and this kind of implication may be the indirect proof of the string axiverse. In particular, from the lattice simulation, we found that the potential bias generated, a gravitational wave. We found a new contribution to the gravitational wave. Avoiding the domain wall problem by small tension, we can actually naturally explain isotropic cosmic birefringence, and this will be tested in the future. And this kind of scenario can be a proof of string axiverse because they are consistent with the decay constant, not very small, around the Carter scale or strings here. Thank you very much.
Thanks a lot, Wen. Any question? We have time for a couple of questions. I don't see hands raising. Okay, well then, just I have a quick question on the last topic, which is birefringence.
Okay.
I also see Javier having a talk. Okay, if I let Javier go first, please.
Thank you very much. So thanks for your nice talk. I wanted to have a couple of questions. So can you go to the slide when you show the spectrum of gravitational waves from the network?
Okay.
There you are. Yeah, you showed two arrows. One is the contribution from so the scaling, or just the domain walls annihilating when they enter the horizon, something like this with others, I guess. And then you the other one comes from domain walls annihilating due to the bias term. Is this true?
Yeah,
and why?
Yeah, we consider this. Yeah. Why? Yeah, because
why?
at this moment we don't introduce the bias, and this is here we have the bias vanishing because we consider time-dependent bias. Therefore, we consider
so there's no bias there.
This is the contribution from the scaling domain wall, and around this figure we turned on the bias, and we found here it increased. This region increased.
Mm-hmm. So, but the bias affects essentially at the end of the simulation, right? So it has nothing to do with the oscillations that appear at the beginning, and you get white noise from this. And sorry, and you said that this is due to let's say additional domain wall annihilation due to the bias, right? So it's somehow accelerated.
Yeah. And I think so. Yeah.
Okay. And wasn't this discussed by Kenichi Seikawa and others, and also in the papers of in the recent papers of Gorgetto and Hage?
I think, if we consider the earlier study, I think in the simulation there is no bias. People usually consider this kind of term, and bias is taken into account by how to say just cut the domain wall, how to say the time to give a cutoff of time to check the gravitational spectrum, isn't it?
Yeah. Well.
Yeah. And also, okay.
And can you go to the next slide?
This is still preliminary. Yeah. So this is a scale invariant case. Yeah,
Mm-hmm. Okay, and then you show that indeed there is a scale invariant with this second peak, and
yeah.
and do you have so I guess so the peak in the ultraviolet is due to discretization errors, but there's a second
yeah, this is not
amount.
physical. Yeah, this is not physics. Yeah.
Mm-hmm. And just below.
Yeah,
What
here should be physical. This region will be we consider to be physical.
But you have also below the very sharp peak in the ultraviolet, you have a not so peak region, like a mound at wave numbers
Yeah.
around 30. Do you know
Around 30.
what is that?
Yeah. Well, I think at least around this region, this will be the peak of due to the mass of the how to say the width of the domain wall, and
Mm-hmm.
yeah, and later this will go to around here, and this should be relevant to the width of the domain wall if if I remember correctly. Yeah.
That's interesting. So you get so from the domain walls, you get let's say gravitational waves that are much softer than the width of the wall.
Much softer than the
right. So the spectrum doesn't start at the mass at the inverse mass of the or at the mass of the domain wall, the inverse curvature of the potential, but it really extends far below.
not below. Yeah, I think usually it is the case, isn't it? Yeah.
Because we have something, so in our simulations of domain wall number equals to 1, right? So the usual QCT Axion case, and we were looking at the Axion spectrum, then we found that so when the potential is very when the let's say when the actions are non-relativistic, and here with the bias, well, here your actions are relativistic. No, they are non-relativistic, right? Some of them. You could form
I think most of
oscillaton.
them. Yeah.
I wonder
This
if
is
you are seeing also
yeah.
some oscillatons in your simulations, and these oscillatons are decaying into gravitational waves as well. And this is another mechanism still.
Yeah. I think in the simulations we see some oscillons. Yeah, we are still discussing about that. That point. Yeah, and yeah,
I suggest then we move on, and because we have
very good.
three more talks, we have another question from Wen Yin, and
thanks a lot.
Yes, you can continue offline. Please.
Yeah, so I have a very super quick question. So is there a plasma during the collapse of the domain walls, or everything happens in vacuum?
Everything happens in.
So is there a plasma during the collapse of the domain walls? Yeah, plasma, the thermal plasma. Or you just consider everything happen in vacuum. There's no any radiation, right, around.
We take into account the radiation in the Hubble expansion. So we didn't take into account the domain wall and the plasma friction or something. Yeah.
Oh, okay, thanks.
Okay, thanks a lot for the discussion.